A modern merchant ship displaces tens of thousands of steel and cargo, pushing relentlessly across the open ocean. From the surface, it appears almost solitary, a silent behemoth navigating the swells. But beneath the main deck, dozens of meters below the waterline, sits a cavernous industrial complex. This is the engine room, a continuous labyrinth of high-pressure steam lines, heavy fuel purifiers, and towering cylinder blocks generating power to keep the ship alive. Operating this environment requires a precise combination of physical interaction and digital monitoring. To train the personnel responsible for these systems, maritime academies utilize high-fidelity engine room simulators. Here, exact digital replicas of shipboard consoles are wired directly to physical throttles, breakers, and alarm panels. Under the strict guidelines of IMO Model Course 2.07, trainees must manage the holistic operation of the plant. Success depends on interpreting how a pressure drop in one auxiliary pump affects the overall thermal efficiency of the main diesel engine. A marine engineer must map these interconnected systems in their mind. The primary objective of this simulation is to build that mental model, ensuring the crew can anticipate and resolve localized faults before they cascade into heavy mechanical failures at sea. Before a vessel can generate power, it sits in a cold ship state. Every piece of machinery is dormant. Fresh water, fuel oil, and lubricating oil are loaded in their respective tanks, but all valves are closed and the plant is entirely silent. Bringing the plant online begins with methodical familiarization. This briefing document outlines initial tasks to identify specific control equipment. Panning down, the checklist mandates testing monitoring systems. Engineers must manually trigger console buzzer and lamp tests, confirming every indicator registers alarms before fluids flow. Once the sensors are verified, preparation of the propulsion plant begins. This execution checklist highlights the required sequence: lining up fuel oil supply, starting primary booster pumps, and engaging the main engine turning gear to slowly rotate the massive pistons for inspection. These deliberate procedural checks ensure the mechanical integrity of the entire system. Establishing the correct flow of fuel and lubrication is the strict prerequisite before the engineers can safely introduce combustion and high-voltage power generation. As the auxiliary systems reach their operating pressures, the engineering team commands the diesel generators to start. The plant transitions from a static state into active power production. Electricity flows directly into the main switchboard. From there, gas-filled circuit breakers distribute 6.6 kilovolt and 440-volt loads across the vessel, feeding the heavy air compressors, steering gears, and stabilizing motor generator sets. The main engine relies on a continuous, pressurized exchange of these resources. Heavy fuel oil is heated and purified. Fresh water circulates through the cooling jackets to absorb extreme thermal loads, and thousands of liters of lubricating oil coat the camshafts and main bearings. Engineers follow this procedure during warm-up, monitor cooling water, verify air pressures, and test steering gear. Then the engine is set for automatic rollover, nozzle valves configured for standby, and the maneuvering lever advanced. Finally, propulsion control transfers to the engine control room. The isolated steel components have synchronized. The engine room is now a single, highly pressurized environment, requiring unified, continuous oversight to maintain stable operation. Crews operate on strict shift rotations. This exercise outlines watch handover protocols. Officers enter 15 minutes early to inspect machinery, using all 5 senses. Digital sensors miss early malfunctions, so engineers must listen for abnormal sounds, feel for vibrations, and smell for leaks. Once the watch is accepted, the routine duties commence. A primary responsibility is the meticulous maintenance of the machinery space logs, recording temperatures, pressures, and tank levels at regular intervals. The watch engineer continuously cross-references the physical gauge readings they observe on the machinery with the digital values displayed on the control room monitors. This ensures the automated systems are accurately reflecting the true physical state of the plant. This continuous physical and digital verification forms the core of safe watchkeeping. An alert crew, applying both physical observation and data analysis, access the primary safeguard against equipment degradation. Suddenly, the cooling water pressure plummets. Alarms trigger across the main console. the primary generator trips offline, severing the electrical load and plunging the engine room into darkness, interrupted only by the activation of emergency lighting. The vessel has lost all main power and propulsion. The team must immediately stabilize the situation, rapidly processing the alarm logs to identify the root cause of the generator failure while the ship drifts in open water. They quickly execute the emergency procedures, switching from remote and automatic control to local, manual control. This isolates the fault and prevents the automated systems from attempting to restart damaged machinery. Following the blackout procedure dictated by the safety management system, the engineers clear the main switchboard. They manually manipulate the transfer breakers in the control room to safely restart a standby generator and restore voltage to the primary busbars. Throughout this sequence, the chief engineer maintains closed-loop communication with the bridge, providing precise updates on their progress to ensure the master can manage the safety of the drifting vessel above. With power restored to the switchboard, the team sequentially brings the main propulsion plant back online. According to this checklist, they reset any abnormal interlocks, manually restart the main turbine, and closely monitor the thrust bearings for abnormal vibration as the propeller begins to turn. Managing a full plant recovery while the vessel is adrift forces a transition from memorized schematics to high-pressure execution. From the instructor station, the assessor monitors the entire scenario. Using this evaluation form, they document the trainees' response times, verify their adherence to the performance standards, and evaluate the logic behind their critical decisions during the blackout. The high-fidelity simulator provides an environment where engineers can push the plant to its limits. They can experience severe, cascading failures and learn from critical errors without putting a multi-million-dollar vessel or its crew in actual danger. Back in the simulation, normal operations are fully restored. The main engine temperatures stabilize, the generators hold their load, and the vessel regains its momentum through the water. Marine engineering competency is a continuous exercise in observation, clear team communication, and decisive action to maintain total control of the ship's mechanical heart.